If you are given the name of an ionic compound and you want to determine what the formula of that ionic compound is, the first step is always going to be to write down the symbol and charge for both pieces of that ionic compound. Now, for typical binary ionic compounds, which have just two elements, one metal and one nonmetal, this is going to be relatively straightforward. So for these three examples here, I have strontium chloride, sodium oxide, and magnesium nitride. So to first figure out what the charge of that element is, I need to look it up on the periodic table. Now, sometimes that element is going to be in a column that has an assigned charge. For example, strontium is here. Strontium is always going to have a positive 2 charge. So for the beginning part of this compound, I can write Sr for strontium and give it a positive 2 charge. Next, for chloride, you have to think what element was this before the ending of the name changed to -ide. Chloride came from chlorine, which has the symbol Cl. When you look up chlorine on the periodic table, it is over here and has a -1 charge. Okay, looking at these two ions, I can see that the charges are not equal. Strontium has a positive 2 charge and chlorine has a -1 charge. To figure out the correct ratio of strontium to chlorine, I have to see how many of each I need for the charges to be the same size. So in order for the charges to be the same size, I would have to add one more chlorine, because then the total negative charge is -2, which cancels out with strontium's positive 2. The charges need to be the same size. So this one would just be SrCl2. The next example, sodium oxide. I know that sodium is Na, and oxide comes from oxygen, which is O. To look up the charges, I just need to look up those elements on the table. Sodium is here, and it has a positive 1 charge. You do not have to write the ones when it's positive 1 or -1. You can just leave it as a plus or a minus. For oxide, oxide is oxygen, which is over here and has a -2 charge. Okay, positive 1, -2. Again, this is not the same size, so they do not cancel out naturally. So I have to add more sodiums to get the charges to cancel out. When I add a second sodium, they now have a charge of positive 2, which cancels out with oxygen's -2. The answer to this would be Na2O. Next, we have magnesium nitride. Magnesium is Mg. Nitride comes from nitrogen, which is N. Magnesium is an alkaline earth metal. It's right here. So it also has a positive 2 charge, just like strontium did. Nitride is over here, so it has a -3 charge. Positive 2 and -3. Okay, whenever you have charges that are difficult to balance like this, you have to conceptually think, how many of each of these do I need for their charges to be the same? So you think, what number does 2 and 3 both go into? What is the smallest number that they both go into? And the answer is 6. They both go into the number 6. So to make magnesium positive 6, I would need a total of 3 of them. Okay, that would give me positive 6. And to make nitrogen -6, I would just need one more. -3 plus -3 is -6. So the answer to this ends up being Mg3N2. All right, well, what if it is a transition metal? If you have a transition metal given to you in the problem, you're always going to have this Roman numeral given to you with the name of the metal. That Roman numeral is supposed to be telling you the charge of that ion, because it's in a part of the periodic table that does not have an assigned charge. The only exceptions to this are scandium, zinc, and silver, which do have consistent charges. So those ones will not always have a Roman numeral included in the name. If it's one of those three, you just know it's +1 for silver, +2 for zinc, and +3 for scandium. All right, so for cobalt, because I don't know what the charge is from the periodic table, it's given to me in the name. So it's cobalt with a +2 charge. Fluoride is just fluorine, and if you look up fluorine on the periodic table, fluorine is -1. It's a halogen. +2 and -1, I just need another fluorine, so it's COF2. Okay, the next couple examples include polyatomic ions. You will know anytime something has a polyatomic ion when either it ends in "ite" or "ate", like this example, or it ends in "ide", but it doesn't necessarily correspond to an element like hydroxide or cyanide. Those don't really come from element names, which means they're polyatomic. Okay, so for this one, because this is tungsten for sulfate instead of tungsten for sulfide, I need to look up the formula and charge of sulfate on a reference. Tungsten I know is W, and the name tells me it's +4. If I look up the formula and charge for sulfate, I find that sulfate is SO4 with a -2 charge. Once you know the formulas and charges, balancing these is going to be exactly the same as before. So I have tungsten with a +4 charge. Sulfate has a -2 charge, so I'm going to need another sulfate to balance the charges to make it +4 and -4. And to show that in the formula, I can't just write WSO42 because it kind of looks like I have 42 oxygens and 1 sulfur, which is obviously not the case. This is when you would use those parentheses. Surround the SO4 with parentheses and then put a 2 after to show that you just have 2 SO4 ions in the formula. All right, next one, aluminum dichromate. So aluminum is Al, and this one does have a consistent charge. It's 3+. Dichromate is another one of those polyatomic ions, and I know that because it ends in 8. Anytime it ends in "ite" or "ate" or isn't an element. So I have to look that up. Dichromate is Cr2O7 with a -2 charge. It does contain chromium, which is why it is named the way it is, and it does have 2 chromiums, which is why it's dichromate. So there are some clues in the name to tell you what the structure is. Okay, so if I have a +3 and a -2, this is going to be kind of similar to the problem I did above. I need to make them both 6. So I'm going to have 2 aluminums and then 3 dichromates. So I'll put it in parentheses, Cr2O7, and then a 3 on the outside to show I have 3 of those. So that is how you handle polyatomic ions. It's not really that much different when you are writing the formulas and balancing the charges. You just have to look up the formula and charge instead of just using it from the periodic table. All right, that's all.